Defines.
Well,
Well,
I think.
well, Hola,
Olivier?
nice to meet you. Keep it simple.
Okay. This is the Hello, it's here. ¿Cómo se termina de hacer el 18?
El 18 lo terminamos en agosto, creo.
Sí, sí.
Los tengo en la mano.
Nacional Fernando que están las listas
Terrible, pero sí, sí, sí. Yo no sé cuántas hacemos, pero por eso tengo acá.
Sí, arriba de la lista de naciones. Maybe a house it's just You're right. No. Yeah, I was thinking so. The seminary is completed by people who are that's very touchable. Yeah. The original person that is very young. Hola, Pablo, no sé, sí, pero entonces sucede de nada. De a veces bueno, les presento a mis colegas en gran, Mónica Opera, es la vicedirectora del Instituto de Astrofísica de París y una de las tres spokespersons de GRAM. Es profesora en la Universidad de la Sorbona y trabaja sobre todo en mucho de su carrera fue en el estudio de la propagación de últimos de alta energía. Trabajó en el laboratorio de Piroget también durante un tiempo. Y el doctor Olivier Martino, profesor también de la Universidad de la Sorbona, investigador del Instituto de Física Nuclear y de Altas Energías de París, y también es uno de los spokespersons de la Operación GRAM. El tercer spokesperson es the other people, Wu Xiangping, Chinese. I speak to remember. Y bueno, venimos a contarles un poco cuál es el estado actual del proyecto, cuál es el objetivo del proyecto y cuáles son las perspectivas que podría haber para instalar el proyecto aquí en Argentina.
Can I remove my mask? Yeah, you sure?
Yes.
Thank you. So hello, thank you very much for inviting us. As Matthias said, we're going to present the ground project, which I include the regulatory inspection project, in the perspective of hopefully bringing the project to Argentina. So the way this talk will be done is that first I will present the general status of the project. Olivier will discuss the technical challenges, and Matthias will discuss more about the Argentina perspective. So ground state stands for Grand Radio Rate Neutrino detection, and so we really are aiming for to use neutrinos to understand the valence universe. So you know that recently, in particular, we've discovered many new valence sources in the universe, neutron star mergers, black hole mergers. We're seeing flares from lasers and stuff. And what we don't understand yet the mechanism of evolution, emission of these objects, and one way to understand them at the sources is to use multi-centers, cosmic rays, gamma rays, gravitational waves, and neutrinos. And neutrinos play a key role in this picture because unlike the other centers, they are not deflected by a magnetic field. Also, they allow us to see far in the universe. They allow us to see deep in objects. Also, contrarily to gamma rays, which could be produced by leptons, neutrinos are clear, have an acceleration signature, and so these make them very valuable to actually pinpoint the sources of the centers that we can receive, and so find the origin of ultra-heavy cosmic rays, for example. But the problem is that they're very difficult to detect, so they require very efficient detection techniques over very large scales. And of course, neutrinos, with neutrinos, we could reach very extremely high energies that are much beyond the LHC energies that we can probe on Earth. And this is also why, even for a particle physics point of view, is really interesting. So we want to go for this uncharted territory here. So this is the neutrino flux that we know we have been measuring it and know should exist today. So far with IceCube we have measured at neutrinos up to 15 electron volts, but beyond we haven't seen anything. But these neutrinos are bound to exist because ultra-high energy cosmic rays are made by the usual observatory, and while they propagate from their sources to us, these cosmic rays should interact with the cosmic photons and produce secondary neutrinos. So it's a guaranteed flux, and we want to go here. How do we want to proceed? We want to do radio detection of ultra-high energy air showers, and the showers of neutrinos will be produced by this mechanism. So if you have a tau neutrino that comes to Earth, it's going to interact with the ground, produce a tau particle, which then go out of the ground, decay in the atmosphere, and then it's going to produce an air shower in which you have an electromagnetic component, electrons and positrons in particular, that are going to interact with the magnetic field of the Earth, and this will produce an electromagnetic signal that can propagate over several tens of kilometers and leave a footprint on the ground of a few kilometers to hundreds of kilometers. So this is extremely interesting because, okay, if we put radio antennas here, we can detect this signal. And radio detection has already been proven to be a mature technique thanks to experiments like AELA, LOFAR, TREN, Galema. And we know that using the radio footprint on the ground, we can reconstruct the parameters of the primary particle, as well as with Robertine fluorescence detectors. So it's a very reliable technique in principle. Also, the other good thing is that radio antennas are scalable, they're very cheap, and they're very robust compared to more complicated, sophisticated detecting units. So, in this sense, radio antennas are ideal for giant arrays. And also, the good thing is that because this footprint on the ground is of more than several kilometers, we can sample this footprint using an array of antennas that is very sparse. We put one antenna every kilometer square and still have a very good sample. This is why we can go for a giant array. And this is the idea of ground. So with ground, we want to deploy 200,000 radio antennas over 200,000 kilometers square. So this is, compared to the map of Argentina, this is the size in total that we want to deploy. But we don't want to do this in one block, but we want to have about 20 subarrays of 10,000 antennas dispatched around the world. This is just an example. Yeah, with 10,000 subarray is of this side. And these have to be deployed in favorable sites, meaning radio quiet environments, a favorable topography that allows both to have a target with the mountain, the neutrino interaction, and then another side with a little slope that allows to have a screen for to get the footprint. We also need to have easy access for installation and maintenance. And then the other big issue that we bump into usually is the administrative issues to have installation on a proper site. So far, we've made a dozen campaigns in China that were excellent in terms of radio quietness, but and we almost converged to several sites actually, and even to one particular site. But then COVID plus the administrative issues delayed the installation of first antennas, and it has been a little bit complicated. And also for the later phase of 10,000 antennas, we've started to really consider Argentina as being a very good prospect for a scientist for one of those sites. So what can we do with 200,000 antennas? What kind of performances we can hope to achieve? So we've done simulations with end-to-end simulation pipelines, and this is the result that we get. So this is the all-flavor neutrino flux as a function of neutrino energy that we expect for cosmogenic neutrinos in the gray shaded area. So here, the cosmogenic neutrinos, as you know, are the ones that are produced when you have ultra-high cosmic rays propagating from their sources to us and interacting with cosmic photons. Then they produce secondary, very high energy neutrinos, and these are bound to exist. These cosmogenic neutrinos for standard source parameters should sit in this region here, gray region. So this is constrained by the Auger observations. And for more pessimistic parameters of sources, it would be below here. So what ground would allow is to guarantee the detection of these cosmogenic neutrinos for their standard parameters. Then my personal bet is that it's not that the cosmogenic neutrinos we would see first, but rather the astrophysical neutrinos, those that are produced directly in the sources while cosmic rays are accelerated and interact with the background photons inside the source. So this is also what you're seeing by ice cube, for example, and these can produce much higher pulses. So these are laser populations, pulsars, and so these could I think are going to be this is my hunt, my main hunt, the astrophysical neutrinos coming from these populations of sources. And what's very interesting with ground is that we are going to be able to point these sources because neutrinos point to sources that are not affected, and because ground enables has an excellent angular resolution. So it has an angular resolution of 0.1 degree, which is for particles, it's really good. And so it's not very visible here, but so we were the first to ambition to reach the sensitivity here. But then several other experiments projects came up and said that they also wanted to get to this sensitivity, obviously, to become better. But what you can see also is that so these are the three characteristics that are necessary to be able to do neutrino astronomy. This neutrino astronomy in this new multi-sensor era, I think, is fundamental. And this is what we need to do in the next stage in high energy astrophysics. And so you need an excellent sensitivity, field of view, and angular resolution. And actually, so ground is excellent in the three, would be excellent in the three characteristics. But for example, all the in-ice experiments, they have a very poor angular resolution. You probably hear a lot about ice cube Gen 2 radio, which is planning to reach this sensitivity here as us, but the angular resolution is 2 times 10 degrees. This is like, you don't do astronomy with this. So, okay, it's great, it's complementary, we would like to have both, but okay, we have a ground to play on with ground. So we also have a very good X-axis resolutions This is what enabled us to compute the composition of the primary particles and energy resolution. So this is great in terms of ultra high energy neutrino astronomy, but we also have with grant a much larger range of science ways. So we can also detect ultra high energy cosmic rays in the same sense. We have hadronic physics. We are planning to also do neutrino physics, ultra high energy gamma rays, and radio astronomy in a novel way by actually summing the unphased signals and be able to scan the whole sky in radio for radio transients, such as fast radio bursts, to quantum populations of fast radio bursts. So with ground today, we are about 90 collaborators from 11 countries. You can see here that there is a little bit of Argentina. There is a quite strong group in Rio. We have groups in Karlsruhe, Paris, and Nijmegen in the Netherlands, Penn State, and quite a strong community in China. And we are today we managed to be quite well considered in the astroparticle community. So, for example, we are in the midterm review of the European astroparticle strategy right now. And one thing that is of interest here is that we are also in the roadmap in the recommendation of Latin American strategy for research infrastructures and physics. And we also have care about environmental impact. And I'll give you the
Okay, yeah, so this introduction by Kumiko, I will try to focus on the various stages of the project and maybe more particularly on the really one column, which is ground photophotometer. So the idea is we really wish to have three distinct phases. So the last one, where we have the full detector deploy is basically the one for which Kumiko presented the expected results. As Kumiko said, it will be composed of 20 subarrays, and the total price tag is about the same. So something which is in the same range or order of magnitude as IS3. So probably something which is, of course, it's expensive, but still realistic. And we hope to reach this rather modest price tag, modest of course, thanks to let's say a kind of industrial approach, simply by duplicating the previous stage with 10,000 antennas, which would be the one where we definitely validate the design and trigger and the data collection. And so this phase, we hope to start it in 2025 and maybe deploy it in 2027, 2028, start data taking in 2028. And so it will be more expensive because we will not be able to completely finalize and reach this industrial stage. And this will be on the present stage where we're really working on now, which is ground photophotometer, which is the one I'm going to talk. So ground photophotometer, the idea is simply to prove that the detection concept of grant is actually valid and working. And to do that, there's two main issues that we have to solve. The first one is to show that it's possible to actually detect and reconstruct, identify air showers only with radio. Most of the experiments today doing radio are using other detectors to trigger, and here ground is going to be so large that we will need a self-trigger system. So we'll talk a bit more about that later. And the second aspect, the second point is that once you have shown that yes, you have an air shower, you need to construct the primary particles, meaning energy, direction of origin, and nature of the primary. So that's what we want to do with ground photophotometer, and how we're going to do that, we're going to use the specific characteristics of the radio signal. So just to get you a hint on what this means, the frequency range where we hope to have, or we know that we will have most power coming from simulations, such as the one produced by ZIRES. The frequency range, so for these pulses, is 30 to 200 megahertz. The pulses are very, very short, with durations below 100 nanoseconds. You have here one example of a pulse recorded with TREND, which is the seed experiment for grant, which was running in China from 2009 to 2013. The amplitudes, of course, it depends actually linearly with the energy of the primary. but the threshold that you can expect is actually bound to the background you measure. And the background that you measure on Earth is dominated in this frequency range by the emission by the galaxy, which has a noise level of typically 20 microvolt per meter over that full frequency range. So if you say that you want a pulse which pops out of this level, we need to be 3 to 5 times larger than this stationary noise, and this brings you to something around 100 or more microvolt per meter. And if you translate that in energy threshold, it's about 10 to the 16.5 p. So that's one point. The other point, which is important and useful, and I will come back to that actually, is the fact that this emission, because of pure relativistic effect, is focused in the forward direction. And you also have enhancements around the Cherenkov direction. And the reason why we go up to 200 megahertz, which is much larger than what is done with Roger, for example, is you need to grab this Cherenkov code, which is a very specific signature of air showers. So using this specific feature, we hope to be able, and we know that simulations show that we should be able to pinpoint and tag air showers. That's going to be one of the main features to actually disentangle noise from air shower signals. Okay, so that's what we hope to do, and to record the signal, we need to use the ground protocol 300 experiments, which is already fully funded by China, with 100 units already built and waiting for us in the warehouse until we get the clear of COVID and get the authorization of development for deployment. Here is how it looks like. So you have the active part, which is the antenna, with 3 arms perpendicular, allowing to measure the full polarization information, which is another very specific signature of air showers. So these 3 arms, they have each arm has a total length of 1.2 meter, so it's quite manageable in terms of mechanics. It's a total pole of 3.5 meter, and at the bottom of this pole, you have these electronics, very fast sampling, 500 megasamples per second, allowing for a fine digitization of the signal, and a Wi-Fi transfer to a central APU room, allowing for a very large bandwidth, and thus allowing to collect all the data without any dead time. And the layout that we will use is such as this. So it's going to be 300 antenna, this is the name, over 200 square kilometers, so about 10 to 15 kilometers wide, this shape. And because of that, the energy range that we can reach, as I said, is 10 to the 16.5, the lower bound, up to the 10 to the 80 units area. So the status now, as I said, is that we're kind of stuck with COVID and administrative issues, so we don't have the way to deploy 300 antennas in China. And what we're going to do to gain time is have a very small array, which can be done, let's say, kind of under the radar, with 13 antennas. We're also going to have 5 antennas, which are going to be deployed this summer in Nancy, the radio territory of Nancy, which you may have heard about. That will allow us to work here in Europe, I mean, not here, but there in Europe, to work actually on data, because China is not accessible to foreigners right now. And in particular, work on these trigger issues that I was mentioning. Yeah, let me just come back to this specific issue. Why is it a problem, this triggering? Simply because apart from air showers, you have many other sources that may generate transient pulses such as this one. And in particular, those induced by high voltage power lines and things like that. And you need a way to actually make this discrimination. These type of shapes, the polarization information is also some features that allow us to actually make an active discrimination at the trigger level. So that's what we're going to try in Nancy. And the other point that I should mention is that there's also a plan to deploy 10 antennas on the OG site. We're going to submit a proposal in that sense to actually start working here in Argentina and hopefully do some cross-calibration with the OG events. Oops. Okay. Okay. So as I said, that's really a key tool to actually prove that we can do that we can run grants. So it's going to be important to show that they are able to reconstruct the spectrum, the arrow direction, the composition of cosmic rays, because 200 square kilometers is fine for cosmic rays, but it's much too small for neutrinos. We will have to focus on cosmic rays. And the good thing is that in this energy range, all this information are pretty well known from other experiments. So just comparison to known results will allow to validate, show that we know what we're doing. And it's also going to be a test bench for further ground stages, and as I said, try to improve the trivial scheme and maybe go to lower data rates, do a better selection at the early stages, and get rid of Wi-Fi, for instance. Wi-Fi is very expensive in terms of funding. It's very demanding in terms of power, and therefore, if we're able to go for, let's say, less demanding techniques, probably we can cut the price significantly and cut the power request. But Drone Proto 300 will not only be a detector, not only be a test bench, not only be a demonstrator, it will also be a nice tool to do physics. And in particular, this will be true if we are able to complement the detector with particle detectors. The reason for that is that in drones and Drone Proto 300 will focus on very inclined showers, because that's the ones which are correspond to neutrinos. And for these very inclined showers coming from cosmic rays, because we are only looking to cosmic rays in Drone Proto 300, yeah? So for these cosmic rays, all the electromagnetic components get absorbed in the atmosphere, and then on the ground you are left only with the muonic component. And this means that we will measure muons with the ground array and electrons with the antennas, because as Kumiko said, radio antennas the radio emission is only associated with electromagnetic particles, electrons and neutrons. So for each shower, we will have a pure muonic measurement and a pure electronic measurement. And this has been shown that this is probably the best way to actually have a proper determination of the nature of the primary. So we hope we can do that in the energy range between 10 to the 6.5 to 10 to the 18 eV, which is exactly where we hope that there is this transition between galactic and extragalactic sources of cosmic rays. And therefore, we hope that Drone Proto will be able to help us and understand this transition together with other experiments such as the Auger prime. Okay, I think I'm pretty much done for the presentation of Drone Proto 300. I give the floor to Matthias the last one.
So from this idea of bringing the project to Argentina, came to me after seeing in a play trip how beautiful and sparse was the land in the San Juan area. It was like I was working on this project and I saw this place and I said, this is the perfect place with a grand site. So I have been working on that since 2018. I do installations and working on the project. And now we are to the point where we will bring, we might bring it to a collaboration and let's say 10 antennas to the first site to start having a presence in Argentina, to do presentation with the talk there. But the objective of my hope is to be able to bring a 10,000 antenna site to the camp. So to be able to host one site like this, what we need is 10,000 square kilometers of land, possible contiguous, but not necessarily. It needs to be all in the same place. It should be close by, but it doesn't need to be one block. It should be a very quiet site, so with a very low baseline, not continuous emission, and also without impulsive noise. So hope, in the best case, far away from power lines or from human settlements, with a topography that is favorable for detection. So we need some mountains so that we can see the tau conversion in the mountain and the shower exiting from the direction of the mountain, so that you don't confuse them with concrete. Because if you see something coming from mountain, you are sure that it's something. It's not. That will make the identification problem much easier. We could do it on a flat area, part of the mountain, that would be possible. But then the identification needs to be done by looking below the horizon. You need to look for events coming upwards, so you are sure that what is coming from there is an entry. So you lose a little bit of exposure if you don't have mountains. But in ways it will be done. It's a matter of balancing how well is the site for other aspects, with how good it is for making the text. We need to have access to the land. It has to be sufficiently remote to don't have noise, but not as close to civilization or to populated areas, so there is a lot of regional. We will need local support for getting funding, for getting access to the land, and another research. And the idea for the 10,000 antenna space is to start in 5 years from now. So it needs to be something that can be done in this time. And the reason for this is that there are other experiments being proposed to tackle the same science case. So if it takes too long time to reach this stage, it will be any longer as interesting. Either first, to get this kind of ultra high energy. Still be done, but it will not be as fast. So just from looking at satellite images, Jerry, and by talking with some colleagues in the collaboration that have previous experience in looking for sites in Argentina, we have identified 4 or 5 possible sites in Argentina that could fit such a large observatory. One could be to the northeast of the Malargüe site. There is a big area there that could host us. Then there is another area south from the Mendoza capital city, south and east, that is also very devoid of population, so that would be interesting. These two sites, especially this one, maybe is too far away from the mountains, but you would have to run specific simulations for this site in order to decide if it is doable or not. And then there is this site in San Juan that has the disadvantage of not being, so each of these areas that I am showing here, it's about 20,000 square feet. So it's twice what we, but take into account that you will not be able to use it all, because if you have a road, you have to cut a part. If you have our line, you have to cut like 2 kilometers around the lines, you cannot deploy. If you have a small town, you cannot deploy in small town. So we are looking for sites that are bigger than 10,000 square kilometers, so that then we can cut. So in the San Juan area, we have these 2 valleys. Here, this is the Calingasca Valley. Here is the Leoncito Observatory. You know. And here is the San Juan capital city. And then around here, there is a very big desert where there's almost no human presence. There's only a small town called Mogna in the middle, and then the rest is the void of population. this is the site that we have gone visiting last week. So we went there to make some measurements on the field. This is a picture of the area close to Leoncito, to the observatory. This is called the Barreal Dry Lake. So you can make you can write the lake in a tab. And we have been making measurements to try to see how the electromagnetic environment works. So we carry with us two antennas, oscilloscope, and data acquisition board from the GP300. So one of the GP300 electronic units, how we have been making measurements with it. We found that the site is very, very in terms of background level, but we have found some pulses that we still have to try to understand what are their sources, because we found them at every site that we visit, exactly the same pulses. So we are doubting that it's something that was in our car or with us that was emitting and that we didn't know. So because it doesn't make any sense that we have exactly the same noise at all the levels, at all the sites separated by hundreds of kilometers. But this is something I will have to confirm. If we confirm that this was a problem with us and not with our equipment, this would be a very, very good sign. And if it is not, we don't confirm this, it's a very bad. So we really have to work. Maybe, yeah, we have nuclearized in God, but yeah, it's very weird because it's one pulse every 5 microseconds continuously and with a fixed height. So it's here that there is something I don't know from the airport that is reflecting on the atmosphere and coming back. And we are seeing it everywhere because we have found it in places where you have mountains all around you. So we are not on the line of sight of any power line, on any antenna, communications antenna. There's nothing there, and you still keep seeing these pulses. So I don't know. We have to make more tests to understand what this could be. Maybe make more measurements on different sites with the same equipment to see if we go to Malarway and we see the same thing. Then it's our equipment. We don't. So this is what we have been doing this weekend. The site of San Juan was the first I wanted to visit because we already have this huge area to start from, but also because there is already existing infrastructure. We have the Casleo site where we could start our base of operations. They have a local know-how, there is a community there. They have the University of San Juan people working in astronomy and in engineering, a lot of experience in engineering. And they have now in progress the installation of the CART radio telescope. The CART radio telescope is the Chinese Argentinian radio telescope. It's a 50 million project that is being installed there, where Argentina puts the local infrastructure and they make the foundations of the satellite, and China buys the antenna and installs the antenna. So since we have a very strong community, Chinese community inside the experiment, and the Chinese are already paying for the detectors of the GP300 phase, it felt natural that to be included in the same collaboration framework that they already have set there. And also because they are the same Chinese institution. Our colleagues in China some of them come from the overseas, the National Astronomy Observatory of China. They are the same people that, the same institution that are putting back project. So this would make the political part of bringing the project here easier. And the other thing that Samsung has is a very strong science and technology program. We have a program based on 7 pillars, and one of these pillars is astronomy. They want to make an astronomy hub in the province, and for them it's very interesting to, or would be very interesting to have an additional project of this size in the north. The disadvantages of the San Juan site that there are is that, especially on the Calingasta Valley, the one that was on the left, there's more people, more small towns, and there are many power lines that are there to provide power to the mining activity that we have on the lands. So this is the smallest part of the site. It's this region here. Here is Oloncito, and we have these 3 small patches where we could deploy. But probably in this area, there are some part of this region that we cannot really use. We have to do a measure, like do more detailed measurements close to the power lines to see how far away we need to go. But in any case, this size of the site is already big enough. We deploy there limited. So, and the other difficulty that I see is that even if the San Juan University has a strong astronomy, or some astronomy researchers, they have none in astrophysics. So we will need to build an astrophysical community. And well, the other thing is that deployment in some areas where we are too close to the mountains can be. So for the 10,000 place, there are a lot of opportunities for collaboration, for where to participate. We have many things still to be done, or starting development. So we are looking for partners there to work with us. I will not go into none of them, but for example, we still need to develop the reconstruction procedures of the events. So to go from the signals that we record to reconstructing the properties of the showers that produce the signal. And we have a lot of experience doing it in Alger, but not so much doing it highly inclined showers. So there is a lot of new algorithms to develop there, and also to deal with a site that will be not contiguous and that we have holes in it. So now the experience that we have in Alger is like we have an analytic observatory with some holes on it, but it's not it's not the main characteristic of the site. Like it's mainly analytic, and we will have to learn how to deal with having patches of the observatory without them. And finally, the development that has been going on in the last month, I would say, is that since we are the original objective was to bring 10,000 antennas array to Argentina, but now it's starting to look like we could also bring here the prototype, the 2,300 prototype or engineering our So since it's taking so long to deploy in China, the time is pressing. And since there is this possibility of having already a Chinese collaboration here in Argentina, it might be possible to bring the engineering array already in this stage, or to already have the experiment in the first stage here in Argentina, or to duplicate it and have one in China and one here. So we still wait for the Chinese issues to resolve, but just in case we start deploying something. And for that, the time scale is really short. So we should start identifying a site in the next year and commit to it in 2 years. So that's it. That's the presentation. If you have questions, ask.
I have a question. About the prototype to be installed in Largo,
The 10 stations.
what is the status?
So this is a new idea of the surface is this year when we started seeing that it was being difficult to go to China because the situation in China is a bit close again because of COVID. So we cannot even go there to do testing. So we need to deploy somewhere we can access and we can work. They will put 5 antennas in the say observatory in France, so that the people in Europe can go and play with the hardware there. And then to come to Argentina, it's also like very interesting because we have a lot of other detectors there. We have new detectors, the water tanks, other radio detectors, and you can cross calibrate. So this surface is between here and December last year. The idea is to start right now building a document for the technical board of the collaboration to present. I don't know if there we have a time for that, but that the meeting or the at most the mass. There is people working on this in IT. They are the ones that are getting writing the proposal. We are doing studies to provide the information that the technical board requires, like some simulations. But yes, it would need to be as soon as possible.
Okay, this idea of engineering mobile equipment, I think that the only that install the engineering mobile, there you are going to start later.
That would be yes.
Real.
Yeah.
Otherwise, the conditions will be completely different. I imagine that if you can, let's say, install this array in China, but then you will put an array and then you have to bring down everything. Is that correct? I mean, what is the idea?
The objective of the engineering array is to show that you can self-trigger only with it. That is the main point. Then you can do some physics with it too. Yeah. But from the ground point of view, from the aim of the thing, what we get from there is to show that neutrinos, the inclined showers, very inclined showers can be detected with radio. You can do that in a place. If you think in the long run, we are looking for 20 sites, not of the one. So some sites will not have an engineer. It's part. And the other thing is that a 10,000 kilometer site, it's so big compared to 300 kilometers, that even if you have in one part of the array and in an array, the conditions in another place So it's not so clear. Ah,
And then another question is concerning the timeline that you said 1 billion, 1 billion array, 4 years to deploy the complete array.
mhm.
But the site is huge. How are you going to deal with the landowner? Because it's not very much better for example, for 5 years or even more, because you have to install in the land where
Yeah, that's why we have to start developing the foundations of the site as soon as possible. It's true. We've been speaking with Team yesterday about that and what was the experience that they had and how they solved it. We thought it was solvable, especially if you have the, the support from the government of the province. That I think that we will get. We met with the minister of the secretary actually of science.
yeah,
and-
you have to discuss with the landowner.
Yeah. And then you have to. Yeah.
I like very much this idea of using the Andes mountain. I think that this is beautiful. So I will go for
Yeah, I mean,
I think this would be
it has other benefits. So if you really want to push something close to the end, especially for Japan, because having mountains on both sides of your site shield you from radio interference from other places. So it has also this benefit. And also deploying the vectors in a slope increase your precision in the construction in the direction because your stations are different altitudes and this gives you a better level arm for the tip of the direction. So it has a lot of advantages it is more complicated to deploy because deploying on a mountain is more complicated than on a flat land. It makes more complicated the construction. Flat is it's more symmetric, I would say. You have to take into account that every station is different, every station is different scale, and all that, but it adds richness to the data. So, so it will be very good to be at least to have one mountain side. I would say that is
Just to complement on the issue with the landowners, we're quite aware that this was really a difficult task in Alger, and we foresee that it could be the same in ground. I think one of the differences is that the imprint on the ground will be much smaller. It will be in principle just one pole, so basically zero impact on the ground. And there's no need, for example, to bring the truck with water. So just coming with a car, you do the foundation for the pole, then you set your electronics. And one thing that we will really work very hard on in the next years is to ensure the reliability of the setup and make sure that the fail rate is really, that sounds a bit negligible because it's impossible, but low enough so that most stations we don't even need it. We're going to run for years without anybody in there. At least that's good. So I would say that the request on the ground is much weaker than what was the case.
The other thing that the ministry, the secretary of the ministry said was that possibly because it's such a deserted region, we saw that the land patches would be very large, so
very
there are
few landowners.
few landowners in the region that we would
sometimes these are the most difficult. Sorry, but
Yes,
that's all of these
Yeah,
problems.
it is true. If you have one landowner that has a lot of land and says no, and then you're in trouble, right? So that's but you don't know until you try.
I think there's one last point is that we are going to try to expand the science case and the support for the project by linking to other IPs. For example, Yeah.
It's crucial. That we talk to the people about science and we really
We met with a biologist who's studying movement of population of animals, and we came with the idea that possibly we could equip them with emitters and we could track them along the array, their movements, by connecting to the antennas. So in principle, if there's an emitter which is in the same frequency range as the antennas, it's possible to track them and follow them basically live. So this is, of course, a very early idea, but this kind of thing, it helps a lot because for the province and for the biology community, it allows them to find interest and support.
Chao, gracias.
Sí, volvemos luego.